So I, along with Rui, is going to take you through the portions where we'll present the advancement made in key phrase extraction and generation using neural methods. So here we are. So just to remind all of you that we are over here, we already looked at some of the traditional methods for key phrase extraction. Now it's time to dive into the modern approaches primarily driven by neural networks. So with the advent of neural networks and especially deep learning, the major change that came along with is the rich representation learning. So model neural networks are capable of learning rich semantic and distributed representations of text versus local representations learned by traditional techniques. And this has led to significant increase in performance of many NLP tasks, which also includes key phrase extraction and generation. So one of the other advantages of neural approaches is that they don't require feature engineering, and it's pretty much end-to-end learning directly from the given data. And this has been leveraged pretty well by the Keyphrase community. So in this section, I'll be mainly covering the neural keyphrase extraction part, and Rui will cover the neural keyphrase generation part. So if you just look at neural keyphrase extraction, it can be further divided into supervised and unsupervised methods. Most of the unsupervised methods are graph-based ranking methods, and then most of the supervised methods are key phrase extraction treated as a sequence leveling task. So we'll first have a look at the unsupervised neural extraction, key phrase extraction methods. So here's a rough timeline of unsupervised key phrase extraction methods using neural representations that I'll be going through. As you can see that the use of neural representations for unsupervised methods have already started as back as 2014. Then there was a long gap of 4 years, and it is only when word embedding models like what2vec and fasttext became popular that there was a surge in methods using them, namely key2vec, embed-rank, and RVA. And then right after the popularity of the contextual and especially transformer-based language models, the community came up with methods that leverages these very rich semantic and syntactic representations of text, which they got from the large pre-trained models like Elmo, BERT, Robata. So now if we look at the basic framework for unsupervised key phrase extraction, it remained the same as presented in the earlier presentation by Florian. What changed is the heavy use of rich neural representations and way to leverage them in the candidate selection and the ranking process. So one of the common themes of these models is that the majority of them also apply graph-based ranking. So let's look at the methods one by one. What Wang et al. Did in their paper back in 2014 is as follows. So they basically used word embeddings as background knowledge, which understands semantic relationships between words beyond the local context of the document. So they used the Senna word embeddings, which were then very famous. They came up with a new weighting scheme for assigning informativeness and phraseness scores of words using word embeddings, plus local statistical information. So they constructed an undirected graph of words with edges determined by their co-occurrence and then ranked it using PageRank. Except what was different from the traditional methods is that the word embeddings played an important role in determining the edge weights. This work also motivated the next work, which is Key2vec. Now let's spend some time on Key2vec in order to understand some of the stages that are common across all the unsupervised key phrase extraction methods that we will see going forward. Now, one of the first steps is candidate selection. In Key2vec, the authors only select the noun phrases and named entities for candidate phrases after cleaning them using a long set of handcrafted rules. They train a phrase embedding model using fasttext after processing a large corpus of scientific papers from archive. Using the same text processing rules as used for candidate selection. Then they represent each of the candidate phrases using the latent learned phrase embeddings. After that, they construct a theme vector to calculate similarity between the vector representation of the candidates with that of the theme, which helps them to assign an initialization score or bias to the candidates. So the theme vector is calculated by taking the candidates from the title of the abstracts and the papers. Now then they form the same graph as Wang et al. As previously described, except this time they use their own trained embeddings and also bias the page rank process by the candidate scores calculated in the previous step. Finally, they rank the candidate phrases using biased page rank or personalized page rank, which they call as theme biased page rank. Now going forward, we'll see that all the unsupervised free key phrase extraction models using neural representations basically have the following steps in their pipeline. So you have an input document or text, and then that gets processed by several steps like candidate selection, reference selection, candidate and document representation, and candidate ranking. So most of the candidates and document representations are made using some of the commonly used word embedding or document embeddings. So initially, most of these were done using some of the fixed embeddings or popular fixed embeddings like word2vec, fasttext, glove, doc2vec. But now going forward lately and recently, most of them are using the transformer language models. Now let's look at embed drag, which applies very similar methodology as key2vec. Except they represent the n-gram phrases now and the document from which they are from the document which they're extracted in the same embedding space using send2vec and doc2vec, with send2vec giving a better performance overall. When it comes to ranking the candidates, they simply rank them by calculating the cosine similarity between the individual candidates and the document vector. This led to a lot of semantically same and redundant phrases being ranked higher. Therefore, they applied maximal marginal relevance in order to bring diversity in their final results, which they call as embed rank plus. Now, embed rank plus did not perform as well as embed rank according to the automated performance metrics, but on a small sample of annotations by humans from 2 datasets, it was concluded that the humans preferred diversity and liked embed rank plus over embed rank. RVA, short for reference vector algorithm, applies the same concept as embed rank with few exceptions. So their preprocessing of text for candidate definitions is different from embed rank. Then they train local word vectors for each document using glove embeddings. They create a reference vector just like the theme vector in key2vec by finding the mean of the representations of the unigrams from the title and the abstract of the papers. And they finally rank the candidate phrases on the basis of their similarities with the reference vector. CIFRank is one of the first algorithms that used contextual language models in an unsupervised ranking setting. The main motivation behind using them is that they can introduce external knowledge and additional features, which the authors assume will improve the performance of key phrase extraction. In CIFRank, in the first step, the document is tokenized and past of speech tags of these tokens are obtained, and then they use a noun phrase, and then they identify the noun phrases and they extract the noun phrases from the sequences according to the parts of speech tags using a noun phrase chunker. And then the sequence of tokens are then processed by a pre-trained language model, in this case Elmo, and representation of each token is extracted. Now, through their sentence embedding model, they turn the embeddings of the noun phrases and document to noun phrase embeddings and document embeddings, and they use especially the CIF technique to do that. And finally, they calculate the entire the cosine distance between the noun phrase embeddings and the document embeddings. Next, KP rank was an extension of key2vec along with positional information for the candidate phrases and contextual embeddings. The authors use the same strategy to construct the graph and use bias PageRank to rank the candidate phrases for identifying the final list of key phrases, except they were now not only biased by the initial scores of the candidates from the team, but also by their positional scores. And they use a contextual embedding model like Sybart. Now, all of this model that we talked about was mostly learning global context. When we were looking at so if you look at the figure on the left shows an intuitive explanation for the importance of what I was saying of context modeling. Now the nodes are candidate phrase embeddings, and the star is the document embedding. So each black circle represents one local context, and nodes in the same black circle mean that these candidate phrases are all related to one vital local information, that is one topic or aspect of the document. Nodes in the red circle mean that these candidate phrases are similar with the semantics of the whole document. So if you only model the global context, which we basically was looking at in the previous works, via computing similarity between the candidate phrases and the document, the model will tend to select red nodes, which will ignore local salient information in the other three clusters. So in order to get the keywords accurately, we should take both the local and the global context into consideration, which was proposed by the referred paper over here. So step by step, so what they do is they tokenize the document and tag the document with parts of speech tags, and then they extract candidate phrases based on the parts of speech tags, and only keep the noun phrases that consist of 0 or more adjectives followed by one or more multiple nouns. Then they use a pre-trained language model, in this case, BERT, to map the document text to low-dimensional vector space and extract the vector representation of candidate phrases and the whole document. And this helps them to capture the global context. But in order to model the local context, they construct a graph between the candidate phrases with the phrases as nodes and the edges weighted by their similarities with each other. Then they apply a new centrality algorithm, which they call boundary aware centrality. And this algorithm takes into account the assumption that they make, which is that most important information typically occur at the start or end of the documents. Now they score each candidate phrases with a ranking algorithm, which jointly models the global and local context, and finally extract the key phrases. And they find that their model can form some of the existing models with generalizing well on the documents with different domains and lengths. And this is the latest paper at ECI at 2022, which I would like to mention over here. And although I'll not be able to go through this paper, but feel free to check out, it seems very interesting. Now let's look at the supervised approaches for key phrase extraction using neural representations. Now, in this space, models treat key phrase extraction as a sequence leveling task is becoming very popular lately. So this is the timeline of the papers that I will be mostly diving into. And as you can see, the current trend is suddenly towards using transformer language models. Now, a good question to ask is, what is sequence labeling? Sequence labeling is about identifying the labels of tokens in a given sequence. So the input is a sequence of tokens. For the models, it would be a sequence of word or subword representations. And then the output is labels for each of these tokens, which could be any of the three in a BIO tagging scheme, where BK is the beginning of the phrase, IK is inside a phrase, and then O is outside a key phrase. And ultimately, the aim is to actually identify each of these tags related to each of these tokens and finally put together the key phrase. So another good question to ask is why sequence leveling? So as we all have seen that there are several issues in the candidate selection process. Different works have put forward different heuristics for processing text and selecting candidates, which affects all the downstream tasks. It is very hard to reproduce the results and there is no unified process. But sequence leveling actually helps is what sequence labeling actually helps is that there are no heuristics involved, not much pre-processing. Then it's an unified process. It allows for optimal assignment of key phrases, and then it also leverages techniques of other sequence tagging tasks and helps us to capture long-term dependencies. So one of the first works in this space looked at just using a CRF for identifying key phrases, in which the authors were mainly driven by two questions. How can we avoid pre-filtering of correct candidate phrases based on potentially erroneous parts of speech tags during key phrase extraction, which is again a shortcoming of the other extractive methods? Can we model the length of a key phrase more naturally in our extraction methods? And this is mainly due to the fact that most of the previous methods relied on pre-deciding the length of the n-grams and missed out longer phrases, which might be more suitable for the document's context. They handcrafted features and trained a CRF reporting good results. During the same time, Zhang et al. Came up with a work that looked at extracting key phrases from tweets, and in their work, they also treated key phrase extraction as a sequence leveling task. So with the input at every step were the word embeddings, and then output at every steps were whether the current word is a keyword, which is basically a binary classification task, and they considered the following option in determining the labels of the words. So if the word is a single keyword, then it would be classified as single, or else the word would be either classified as begin, middle, end, or not, depending whether the word is at the beginning of a key phrase, it's a middle of a key phrase, or end of a key phrase, and not if it's not a part of a key phrase. They came up with a novel architecture of joint layer RNN. Now, with the exception of the work from Zhang et al., later going forward, most of the works tag the key phrases in a document following the BIO tagging scheme. Professor Carrigher's group at UIC looked very closely at the sequence leveling task using CRF and the BiLSTM CRF architectures, and also introduced word embeddings as features. They used the Word2Vec embeddings trained on Google News and also created their own corpus comprising of scientific documents and trained a Word2Vec model on it. Now, some of the natural questions to ask over here are, why word embeddings with CRF? So only CRF with document level features do not capture the semantics of the words in context that are often hidden in text. So basically word embeddings helps you to capture the semantic relationships between words and leverages the semantic representations that learn from a big corpus. So why use BiLSTM with CRF? Now, if you look at the architecture of the BiLSTM CRF, we find that there's a BiLSTM layer between the features and the CRF layer, and the features are not directly fed to the CRF. What BiLSTM helps is to capture the long-term dependencies, and what CRF helps is to learn the dependencies among the labels of the neighboring words. Now, some of the observations that they made were that the CRF with linguistic and statistical features performed better than CRF with word embeddings. And then CRF with word embeddings plus linguistic and statistical features outperform both CRF plus linguistic and statistical features and CRF with word embeddings. And then BiLSTM CRF helps on a large training data. And then BiLSTM CRF predicts long key phrases well, which supports the argument that they capture long-term dependencies. Now, going forward, we looked at using contextual word embeddings, namely the transformer-based language models, and found that they are used when used in a BiLSTM CRF setting, they pretty much outperform the fixed word embeddings. So context really helps. Also, using a domain-specific pre-trained language model such as Cybert helped. Later, another model was proposed which still treated key phrase extraction as a sequence leveling task with a CRF However, they also took into account document level attention. The authors argue that BiLSTM models are good at learning local context at sentence level. However, a lot of contextual information can be obtained from other parts of the overall document. So they came up with a mechanism of document level attention for incorporating relevant information from the other parts of the document with respect to the local context. But this can lead to learning a lot of noise. Therefore, they also propose a gating mechanism to filter out the irrelevant information. Another interesting model was proposed recently, which learns word representations from the pre-trained language models such as BERT, as well as graph embeddings learned from the co-occurrence graph. The final word representations are obtained by concatenating the BERT embeddings with graph embeddings, and then they treat key phrase extraction as a sequence leveling task. Now, current models, which are mostly attention-based models, only exploit the plain text features. They treat input text equally and ignore the inherent context, such as title, sections, main body, or semantic roles like who, what, and how. And this leads to the models paying overweighted attention to the insignificant words. And this work, as referred below, looks at solving this issue using hypernetworks. Hypernetworks are neural networks that learn the weights of other neural networks. So they model the descriptive meta information via hypernetworks. So they extract the descriptive meta information in the meta text for more effective processing of the main text. So in the context of key phrase extraction, they take the title as the meta text and body as the main text. So now meta and main text are then first encoded by a pre-trained language model. The embedding of the meta text is then fed into a hyper encoding layer to generate the weights of the infer encoding layer. Infer encoding layer converts the embedding of the main text into representations for task-specific fine-tuning. They achieve state-of-the-art scores using this strategy, and they show this strategy to be effective for other tasks as well. Researchers from Microsoft came up with a very interesting work that looked at extracting key phrases from the wild, which is actually the way it works in an industry setting. They produce a very rich and a large data set, which we already presented previously in the tutorial, and they also tried zero-shot evaluation of their model and showed that their model outperforms a model trained on scientific data. They also came up with a new architecture, which is multimodal and takes into account both the textual features by learning them using convolutional transformers and also the visual features of the text pieces, which they integrate with the word embeddings. They also pre-train their model with weak supervision from search queries, which they obtain from the Bing search engine logs. They consider query prediction as their pre-training task. What is very interesting in that architecture is that the convolutional transformers can work well even for long documents. They take into account multiple modalities, and they also find that using them really helps. Also, during the pre-training stage, the architecture is capable of predicting query phrases of any length. I think this is really promising and exciting. Some other works that I skipped and I would like to mention are two of these recent works. One is SASEC, which looks at syntax and semantic aware model in order to better model long-term dependencies. And then TNT-KID, which explores fine-tuning transformer models for token classification in the context of key phrase extraction and provides a detailed report of their findings. We have made most of these popular data sets available in made available in Hugging Face in a BIO tagged format. So feel free to use them in your next sequence leveling experiment. Thanks. So next, I think it's time for Rui to dive into neural key phrase generation.